finesse of a concept that's been, kind of a decade or more in evolution. I'm going to focus more on what we can learn just looking at Phobos in terms of the groove structures, because like many planetary scientists, there's these puzzles that just don't go away, and the groove structures of asteroids is one of those puzzles. And there we go. And when I was a kid, or I forget how old I was, I remember seeing this picture, and it was just the most amazing thing ever to me, that something could be so bizarre. And I think a lot of planetary scientists felt the same, who were actually studying this, like Thomas and Duxbury and Viverka and others. And then Mars Express has come along and revealed to a meter per pixel type image frames of parts of the Phobos surface. And you can see these very strange puzzles. You have grooves, cracks, faults, fissures, fractures, whatever you want to call them, that cut right across crater rims and cut right across pre-existing structures as though they don't know that they exist. And so those of you who've studied cratering mechanics know that in a crater bowl like this one, there's going to be weaker materials deposited at the rim and maybe stronger structures, different kind of structural features if it was forming in solid materials. And to have cracks or whatever these are kind of going across crater rims was always a deep puzzle for me. Here's by Murray et al. 2008 or 2006 in later papers, giving you kind of a lay of the land of Phobos. The North Pole. It's an interesting geography. You can actually go on Google Maps and find a KML file for Phobos and Deimos and kind of zoom around and look at them. And it's bizarre to kind of find your bearings. Here's Stickney. Here's the western rim of Stickney, the eastern rim of Stickney, western rim. Here's the North Pole, submars, meridian. And when you wrap this out into a cylindrical coordinate frame, here's oops. I guess I'm running out of juice here. But here's Stickney on the left, and there's the Mars center. And you can see that there's a symmetry with the sub-Mars points. So one of the first ideas that came around for explaining this groove system, especially once we got proper cartography, was this notion that it's related to tides. Because the tides are symmetric to the sub-Mars point, the groove system seems symmetric to the sub-Mars point. Yet there was this tendency, especially in the early 80s, late 70s, to try to connect the grooves somehow to the Stickney impact, which would be the event that caused all these cracks to grow. And those who followed this field closely have found, lots of trials and tribulations in trying to have Stickney itself be the cause of the groove networks. It's geophysically kind of in an inconvenient spot, and some of the grooves actually seem to post-date the formation of Stickney. So let's look at a close-up here. Here's the MRO HiRISE. We have lots of assets looking at Phobos from lots of different Mars missions, no dedicated Phobos mission, as Pascal mentioned at the very start. Ideas. Cracks in solid rock radiating from Stickney. That was kind of the original, one of the original thinking. Boulders rolling downhill, ejecta from Stickney. These grooves are pitted, and I don't have enough time in my talk to go through all these details. Ejecta from Mars craters. This is Murray et al. Hypothesis in 2011 and 2014, where you have Leo crater and other major craters on Mars transporting ejecta into the Mars satellite system and making linear features on Phobos, but somehow not on Deimos. Tidal stresses, talk about those in great detail. Comet-like venting, the notion that there's sort of raised rims around some of these cracks led to this notion that it's degassing from an icy interior. Catena, chains forming in the Martian surface from tidally disrupted objects within the Mars system that might form linear features like the catena on the Galilean satellites from disrupted comets. Drainage pits. Horstman and Malash were looking at the idea that you could pull apart an existing rigid surface shell and have regolith drain in through that shell and get a pit spacing, and that would imply a regolith depth of around 300 meters. And then shear localization, which is just sort of a bandwagon term or a generic term for anything that concentrates deformation along a fault. So all those ideas, tidal stress is sort of the most natural to try to explain this this geometry. And back in the day, those of you who remember back in the late 70s and early 80s, Soder and Harris, and then Dobrovolskis in 1982 looked at body stresses produced by tides and got, as you'd expect, a Mars submartian point center geometry to the tidal stress, but it didn't work very well in terms of the geometry of where the predicted fractures would be. But it also led to the notions of a very weak body, and Soder and Harris have a few sentences about how this might be fractures forming in powdery regolith instead of in actual solid rock. And so fast forward to, a couple of decades later, Terry Herford et al. In 2016, and I don't want to steal Terry's thunder, he's giving a talk tomorrow on this model itself and some later developments, consider a thin elastic shell on Phobos. And now that sounds kind of bizarre. It's like, it's a weak object with a stronger elastic shell in the exterior. And the nature of the model, for a moment, suspend your disbelief that an object like Phobos could have a thin elastic shell on it. And just look at what the assumptions are. And then we'll see whether those make sense. Treat Phobos as a two-layer body. 10 to 100 meters of an exterior, and then the interior is weak. The exterior is stronger. The interior is so weak that it deforms readily due to tidal stresses as Phobos spirals in towards Mars. As it spirals in, the stresses increase, its shape changes, and the shell comes along for the ride and expresses fractures. It's not an elastic shell that holds Phobos together against tides. It's been shown clearly by Holzapfel in 2001, a really great paper, that Phobos would do just fine without any strength whatsoever. All it needs is an angle of internal friction of 3 degrees to not come apart presently. But this exterior shell, what is it? Well, the depth is something that you can base on images. What are the extensive faults, grooves, pits, these kinds of structures? Without putting a lot of interpretation on what they are, you get this idea that there's geomorphology, faulting happening in the upper 100 meters of Phobos. So that's a number we pick based on observations. The elastic modulus of this shell, let's assume that it's a lunar-like elastic modulus. Horvath et al. 1980 did a study of the seismic properties of the outer layers of the moon. There's like a 200 meter per second sound speed in the outer shell of the moon, which can be interpreted as a low elastic strength in some kind of a regolith continuum. We don't know too much what that might mean for Phobos. I'll get to that in a little bit. The interior just has to be weaker than this on the million-year timescales of tidal evolution. And so you have a weak interior that's free to deform, and then you have a shell that is going to express fractures as it deforms. The tidal deformation is computed using the Love number, and today that would correspond to a tidal bulge of around 70 meters. As Phobos comes closer and closer to the planet, the bulge grows and grows and grows. And so you can calculate the tidal stress. This is from Herford et al. 2016. You start somewhere, you end up somewhere. Here's the initial semi-major axis. Here's the final semi-major axis. So any point on this graph is a starting and ending state, and these lines would be the stress going from a starting to an ending condition. So for example, coming from 3 Martian radii to 2.7 Martian radii today, you'd build up a stress of around 100 kilopascals in this surface shell. 100 kilopascals is not a lot of stress, but it's enough to break through a cloddy, powdery regolith of the sort that we know on the moon. By which I mean, here's Buzz Aldrin's boot print. Dust clods up. We make powdered coffee. We play with fine powdery materials in making ceramics. So we know a lot about this stuff, and as you get finer and finer and finer grain sizes, lunar grain sizes are of order 2 to 4 microns, 20 microns in that range. These clump together. If you apply it to a gravity field 1/50th the gravity of the moon, 1/300th the gravity of Earth, you'd say, how deep would these little cracks and fissures extend into Phobos if they were made of the same material? Little Gedanken experiment. What if Phobos was made of powdery lunar regolith? What kind of geomorphic and geophysical structures would we see on the surface? We'd see cracks Apollo astronauts saw fissures in regolith up to tens of centimeters to a meter deep. On Phobos, these would extend to tens to hundreds of meters deep. And so that's the basic idea here, is that you have faulting in a weak substrate. I'd apply that, thank you. I'd apply that as well to asteroid Eros. Here's Deborah Buskowski's work on looking at fault structures on asteroid Eros, about the same size, about the same gravity. I'd say these are not expressions of strength. Cracks on asteroids of this size are expressions of very weak material, very finely comminuted powdery material. I'd say this isn't, this is kind of controversial, but that's why I'm giving my talk. Here's the model of Herford et al. Red grooves correlate, these are mapped grooves, and red correlates very strongly with tensile stress in this shell model. Blue correlates with compressive stress during this present epoch of Phobos. And so the correlation of all these grooves with the tidal stress field, according to this model, is compelling in our opinion. Now there's just inconsistencies. These areas that don't agree with tensile stress, they may be relics from a past tensile epoch in a different orientation of Phobos, or they may be compressive in some way. So the answer's not, it's not done yet. I should note, we've all done this kind of for free, so we're trying to figure things out as best we can. I'm not going to talk about the sesquinaries. These are just other families of grooves that you can form by, in this case, drilled rig, ejects material, goes into orbit around Mars with Phobos, reaccretes back onto Phobos and forms these chains. And this is work by Mikey Nyack, who's here at the conference giving a poster. But what's important here is that for this to work, craters like drilled rig have to form in the gravity regime. They have to form from loose, weak materials. If they form in the strength regime, the ejecta velocities are too high, and you don't reaccrete material in formation the way that you would do for low velocity gravity regime ejecta. So just to end, the idea of a weak elastic shell over a weaker interior seems odd, but actually agrees with ideas of a cohesive, fracturable, powdery regolith structure. They go right through the rims of craters and other structures because those craters are just formed. They're not expressed in solid rock. They are formed in weak materials to begin with. Grooves, as Terry's going to talk about, they might further evolve due to diurnal cycling. And the final conclusion is that it gives you this object which is consistent with the giant impact models, which would form very weak aggregated materials. It's consistent with an asteroid origin because I think asteroids are also made of weak, consolidated, largely rock-strewn dirt materials. And it's also consistent with this modeling of craters forming in low-gravity, weak regolith. Thank you. Oh. Save me the embarrassment. Ask me a question.
How would you form that elastic shell? Why would the outside be stronger?
It's a very good question. The inside, I don't actually think it has to be a mechanical boundary. I think it might just be the transition between above 100 meters, the cohesion is greater than the normal stress, the pressure, and then below 100 meters, the gravity is stronger than the cohesion. And then when you get to this transition, you go from elastic to ductile behavior. I don't think it's quite that simple, but I don't think you really need a compositional boundary. I think it's just a powdery material. Once it gets compactified enough, it deforms more as a continuum. And when it's less compactified, it fractures, essentially.
Maybe you mentioned this, but what is the thinking about the mechanism for the creating the higher elasticity, and would it be either some sort of compaction or just the very light amount of overburden? Is that sufficient? Is it even, less elastic on top, then a little bit more elastic, and then less so, or whatever down below? And then along with that, any thoughts on how that might have changed over time, and so how you might have, or over the surface, so you might see some difference in the fracturing on along either of those dimensions?
Yeah, very briefly, I would say the cohesion is simply aspect of the very, very fine grain sizes. And I'd say it's exactly as the cohesion on lunar regolith. I don't, there's no real chemical bonding or anything like this, sort of like van der Waals forces. So Dan Shears et al. In 2010 had a paper on the, van der Waals cement, the way the powders could hold asteroids together. But I think that's kind of where we're at transitioning in this work right now, is to try to really understand, can Phobos really be made? That's kind of my first operating assumption, is can Phobos be made of lunar-like regolith? Different composition probably, but just start with those basic material properties.
Yes, question?
Okay.